It is an important skill to know how to configure and verify static routes. However, in larger environments, it doesn't make sense for you and I to configure static routes for reachability to every single network. Instead, we might use a few static routes like default routes in certain areas, but most of the time, we're going to have the routers dynamically learn how to forward packets to remote networks using some type of a dynamic routing protocol. And that, my friends, is what you and I get to start discussing right now in this video. And for this discussion, let's have some fun by imagining that you and I are right here. So this is us. And our goal is to get to some destination. We'll call this just DEST for short. So we're trying to get there. And if we're traveling, let's imagine we're traveling by a vehicle, whether it's a bicycle or a car or whatever. And we have two paths. We have the path on the north side and we have the path on the south side. And which one should we take? Which path should we take? I heard somebody once say, if you don't know where you're going in life, it doesn't matter. Take any path you want. But if we want to get to this destination and we have two options, let's fill out the rest of the journey and then we can make an informed decision. So let's imagine that we have a toll booth. That's good. That'll work. So let's imagine we have toll booths. So this will be toll booth number 1. This will be toll booth number 2. And then as we go further, there's another toll booth. And toll booth 3 and toll booth 4. Now, in various countries, those toll booths may have different names, but it's where you're on a road and you stop and you have to pay a little fee to continue on that road. So these are representing toll booths, and then let's put one more and that'll be good. So 3 and 4 and 5 and 6. And then that takes us to our final destination. So based on this, which path should we take? Path A or path B? What do you think? I would like your opinion. Now, you might be saying, well, Keith, if all the costs are equal, let's say it's $1 or €1 or a pound or whatever it is at each of the stops, and all the roads are the same, then it wouldn't matter. I would agree. But if the tolls were different at each step along the journey, then it would matter if we were concerned about cost. So to give us more information about which path we should choose, let's imagine that at toll booth number 1, the cost is $2 or €2 or 2 units. And at toll booth 3, the cost is 10. And at toll booth 5, the cost is 7. And then down here on path B, let's imagine that toll booth number 2, the cost is 3. And at booth number 4, the cost is 8. And at booth number 6, the cost is 7. Now, assuming all the roads are equally good, which of these two paths should we take if we're concerned about cost and getting the best value for our dollar? And the solution to that could be we'll simply add up the cost. So 10 plus, for path A, 10 plus 2 is 12, plus 7 more is 19. So I'll put that in a different color up here. So the cost on this path is 19. Great. And for the bottom, let me make sure I did that right. 10, 7, 8, 9. Yeah. But then path B, the cost would be 3 plus 8 is 11. Plus 7 more is 18. The cost here is 18. So if we were being cost conscious, we could go ahead and choose this path because it would be more cost effective or a better value or a better path. So let's take what we know and apply this to routing. Let's imagine that 1, 2, 3, 4, 5, 6, these devices are all not toll booths, but rather they are routers. When we run a dynamic routing protocol, we enable that routing protocol on each of the routers. It's sort of like running an app on your phone. You turn it on, it starts running. Well, if we run a dynamic routing protocol on each of these routers, that allows these routers to talk to each other and communicate information. And once we do so, R1 will learn from R3, and we don't have to manually configure static routes because R1 can dynamically learn information about how to reach remote networks via R3. And R5 can learn from R3, and so forth and so on, using a dynamic routing protocol. Now, not every dynamic routing protocol is created equal. There are two big categories regarding dynamic routing protocols, and it's based on how they operate. One of them is referred to as a distance vector routing protocol. A distance vector routing protocol. I'm going to put a little symbol here of not so great. And when I think of distance vector, here's what I think. I think, okay, how far is it? What's the distance to get to a given destination? And vector, which direction should I go? So for me, that's the way I remember it. How far is it? What's the distance? And which vector or direction should I take? And one of the most oldest dynamic routing protocols on the planet is a distance vector routing protocol called RIP. Not as in rest in peace, but Routing Information Protocol. And people who are still using it, if they are, they use version 2 for a lot of good reasons that we can talk about later. But I just want to introduce it as a distance vector routing protocol. But it's not, the reason it's frowning here, it's not that smart, because distance vector routing protocol, specifically RIP, it doesn't take into consideration the actual cost of each of the links as we go from our source to our destination. Instead, it just does hop counts, hop referring to every router in the path. So in distance vector routing protocols like RIP, it would say, okay, to get from here to there, I have to go through 1, 2, 3 routers for path A. So I'll put that in red for RIP. How about that? Let me get red out. So from a RIP perspective, it would be 3 as far as the cost. They refer to that as the hop count, each router being a hop in the path. And for path B, it would be 1, 2, 3 also. So RIP would think that path B is also a hop count of 3. And as a result, these would appear as equal cost paths, when in fact, one is not equal to the other. One is better. But distance vector routing protocols don't take into consideration the factor of cost or how effective a path is. They're just looking at hop count in the example of RIP. So the next question might be, well, what's the other category that is hopefully a lot better than a distance vector routing protocol? And I will put a little line here. And the other family is referred to as link state, as in a link state routing protocol. And a big example of that, a really popular example of that, is OSPF. And when OSPF is used for routing for IPv4 packets, it's referred to as version 2. So if you see OSPF by itself or OSPF version 2, they're referring to routing for IPv4. If you're looking at IPv6, they call that OSPF version 3. So the next thing I'd like to chat with you about is how in the world does OSPF, which is an example of a link state routing protocol, how does it do better in making decisions than its competitors like distance vector routing protocols? And the answer is information. And you might say, Keith, what do you mean information? Well, in OSPF, what we would do is we would train all the routers to run the OSPF routing protocol. They would start communicating with other neighbors that they're adjacent to. These routers would start talking with each other directly, but in addition, they would create what's called an LSA. And LSA stands for Link State Advertisement. And link state advertisements are pretty simple. Let's imagine that you and I are on the phone and we're chatting about router 6. And that if I asked you, or if you asked me, hey, can you tell me about router 6? We could say something like, okay, router 6 is connected to, off this interface, is connected to network, let's call this 10.6.0.0. And over on this interface, it's connected to 10.8.0.0 with a 24-bit mask. And other details about that network would be the cost. So that's some of the information that's in a link state advertisement. So here's the secret sauce with OSPF. If we have each router generate link state advertisements, which basically say, yeah, I'm connected to this network and I'm connected to that network, and here's their respective costs. If that information can be forwarded over the whole network so that every router has a copy or has that information from all the other routers, the routers can piece together the whole puzzle. And that gives routers the ability to say, oh, in path A, the cost is, looking at my notes, the cost is 19 from here to there. On path B, the cost is 18. So what that does, it gives routers the ability to collect all that information. They take all those LSAs and they put them into a link state database. It's a collection of the LSA information. And then each router can figure out what the best path is. Let's take a look at the topology. So going back to our topology, if router 6 and router 5 and router 3 and router 4 and router 2 and router 1 all generated their link state advertisements with the information about what networks they're connected to and what the cost is, then a router like router 1 could take all that information, or if this was a router right here, we'll call this router X. If this is a router that has all that data from all the routers, all those link state advertisements, it will know, oh, I see. Router 1's cost going this direction is 2. Router 3's cost in this direction is 10. Router 5 going in this direction has a cost of 7. And this router can add those up and get the cost of 19 for path A. And then it can also be aware, because of the LSAs, all the costs on the bottom path and add them up. And then each router with all the data is going to make a decision. And guess what? It's going to choose the shortest path first. And that's why the routing protocol is called open shortest path first. Every router in the area has all the information about all the other routers in that same area, and then they can make an intelligent calculation on the best path, which includes the cost. And as a result, we can choose better paths as opposed to dynamic routing protocols where cost and other details about the links in that path are not considered. So here's our 3 basic takeaways from this video. Number 1, if we have lots of networks, doing static routes for everything is too tedious, too painful, too much overhead, and if things change, we have to go back and revisit it. Not good. So we use a dynamic routing protocol. And there's 2 categories, or 2 families of dynamic routing protocols. One is a camp of distance vector, which isn't very smart. It has a basic idea, but doesn't take into consideration cost. Like with RIP version 2, it's just counting the number of hops, the number of routers between here and there, and that's it. Now, in contrast to that, there's a family of dynamic routing protocols called link state routing protocols. A perfect example of that is OSPF. With OSPF, each of the routers is advertising the details and costs about their networks they're directly connected to. All that information is forwarded to all the other routers in that area. So each router has a link state database, basically a collection of all that information, and then it starts deciding, just like we did at the beginning of the video, which is the best path. Oh, it costs 2 here, it costs 8 here, it costs 7 here. I will go ahead and use this path because it's the shortest path. Open shortest path first is a very popular dynamic routing protocol that is link state. And also, it happens to be the major topic of all these videos in this skill going forward. So I will see you in the very next video as we take a closer look at the interworkings and details of OSPF. Till then, I hope this has been informative for you, and I'd like to thank you for viewing.